Alright, I'm just going to be going over some of the basics of reflection and refraction so that we have a starting point when we return to our experiments. The first concept is quite straightforward. It's the concept of reflection, and we're going to have a look at the simulation here. If we have a laser light and we shine it at a reflective surface, then we'll get some of the energy reflected. If we draw in a normal line, which is a line that's perpendicular to the surface running through it, then the reflected ray will always obey the law of reflection. And the law of reflection says that the angle of incidence, so the angle that the incident ray makes with the normal, is always equal to the angle of reflection, i.e. the angle between the reflected ray and the normal. So in this one we can see that the angle of incidence is about 53 degrees. The angle of reflection is about 53 degrees. And that's always the case. So as I change the angle of incidence by moving the laser pointer around, we can see that the reflected ray changes so that the angle of incidence always corresponds to the angle of reflection. The second part of the law of reflection says that those three lines are all in the same plane. Of course, this is a computer screen, so they are all in the same plane. But in any real-life experiment, this incident ray, this reflected ray, and that normal would all have to be drawn in the same plane, so even if it's a three-dimensional thing. Okay, there's nothing more really to reflection, except that when we do our experiments, we'll actually first have a look at what happens with water waves. And water waves actually are easier to see if we look at them as a series of wave fronts. So you can imagine a wave either as a ray, which is what we looked at before, or a series of wave fronts. And the wave fronts will be reflected at the boundary so as to produce an identical wave that propagates on. It's dimmer here because this is taking into account a few other details. It's not a perfect reflector, this water surface. Okay, so that's reflection. Our next concept is the concept of refraction, and I'm going to start by looking at it with the laser line directed exactly along the normal, so perpendicular to the surface. And refraction is what happens when waves move from a medium in which they travel at one speed into a medium in which they travel at a different speed. If that happens, so if the wave changes its speed as it moves across a boundary, then refraction happens. And in this instance that I've got lined up here, I have the light wave traveling vertically through a horizontal surface and into another medium, and the wave slows down as it does that. And there's nothing that we can see when we have it represented as a ray, but if we look at it as a wave, we can see that as the light waves travel quickly here, when they enter the slower medium, the light waves slow down, the wave fronts move more slowly, which means that wave fronts that haven't yet entered kind of catch up with the ones that have already entered the slow medium. And that results in a shorter wavelength in the second medium. So the wavelength gets shorter as a wave moves from a fast medium into a slow medium. And light waves travel at their fastest in air, actually in a vacuum, but air is pretty similar to a vacuum in terms of the speed of light. And they travel much more slowly in water. Okay, one other thing that I want to mention, it's going to come up later in the notes, but I might as well mention them now. Just how much more slowly the light waves travel in water is measured by a factor called the index of refraction, which is 1.33 for water. And the index of refraction, or refractive index, is just how many times more slowly does the light travel in the medium than it does in air or in a vacuum. And it's 1.33 times more slowly. And we'll have a look at that as an equation. So the refractive index tells us how much light slows down in a particular medium, and it changes depending on the medium. So if we look at glass, we can see that it slows down even more. So we have a refractive index of 1.5. Water is 1.3. Air is 1. So if it goes from air to air, then there's no change, and there's no change in the wavelength either. If we look at something with super high refractive index, or maybe we can change it here. The highest one, you can see that it slows down even more. Okay, so that's refractive index and that's refraction. Refraction leads to some interesting effects when light enters a medium at an angle. If I change the angle at which I'm shining the laser, so I'll change it like this, what you can see is that light travels in one direction as it enters the medium, but then as it crosses the boundary it changes direction and travels in a new direction. So we can use this protractor to get a sense of what this means. Our angle of incidence here in the fast medium is sort of 54 degrees, but our angle of refraction, which is the angle between the normal and the refracted ray, is only about 32 degrees. And so when light travels from a fast medium into a slow medium, we say that it bends towards the normal. And just how much it bends is something that we're going to have a look at using something called Snell's law. Okay, you don't need to worry about filling out page 52. We'll work through that with the ripple tank the next time we see each other. You can have a go at these questions. The answers are published on MyKristin, so you can give it a go and just see if you've understood kind of what we've gone through so far. Now here's what I was talking about with an equation for the refractive index. So the refractive index here of glass, for example, let's make it glass, is 1.5, and that tells us the ratio of the speed of light in a vacuum divided by the speed of light in the substance. So in this case, the speed of light in a vacuum divided by the speed of light in glass. The speed of light in a vacuum is always 300,000 kilometers per second, or 3 times 10 to the power of 8 meters per second. And the speed of light in glass is much slower than that. So that means we end up with a number n that's bigger than 1, because we have the number 300 million here divided by some number that's smaller than 300 million, which means that n is always going to be bigger than 1. And light never travels faster than it does in a vacuum. Okay, so just to check that you've understood that, you can answer this example here. Just pause the video. Okay, so then the next concept is, this is really the concept that you're going to need to work at the most, and that is Snell's law. So Snell's law basically says that, it tells us the relationship, because there does look like there's a definite relationship between the angle of incidence and the angle of refraction, and there is. That's that the sine of the incident angle divided by the sine of the refractive angle is always equal to a constant number for any given interface, so any given boundary. So if it's a boundary between air and water that we have and it's flat, and we shine a laser light into it, and we take the sine of this incident angle and we divide that by the sine of this refracted angle, then we'll get some number regardless of what angle we use, right? That number remains constant. Okay. And so we can represent that in a number of ways. So we can either say the sine of the incident angle divided by the sine of the refracted angle is equal to a constant, or we can say sine theta 2 over sine theta 1 is equal to n1 over n2. So these two n's are the refractive indices of the two media. So if we have air and water, then n1 will be air and n2 will be water. Theta 2 will be the refracted angle and theta 1 will be the incident angle. And then if we have only one unknown there, we'll be able to solve for that. So we can use this to figure out for example, by measuring angles, we will be able to figure out the refractive index of a material. Okay. To get your head around this, there's only really one way, and that's to practice applying it. And so to practice applying it, what I suggest you do is to make measurements here for each one. So maybe you can check with glass. Oops, we want air to glass. Just check that you get the correct answer here. You should have a refractive index of 1.5. So in this case, theta 1 is, we can make it something really nice. Theta 1 is 30. And if theta 1 is 30, then theta 2 here is 20. And we know that n1 is 1. and we know that N2 is 1.5. So what you can do is just put those numbers in and just double check that corresponds to Snell's law. And once you're comfortable with how to do that, I want you to design an experiment to figure out what the refractive index of mystery material A is, and then what mystery material B is. You can help each other out in doing that. But the next time we see each other, I'm going to ask you what the refractive indices of mystery materials A and B are. Okay, cool. We'll resume looking at refraction in more detail and using the wave tank that we have on Tuesday. So have a great day, and I'll see you then.